So welcome everybody to the webinar of today. This is the first webinar of the new semester for the LMFL webinar series. And the speaker of today is Joseph Klewicki. I hope I pronounced it well. And he will talk about properties of turbulent channel flow similarity solutions. So as usual, I introduce the speaker very briefly with a bio sketch, and then I leave him the floor. So Professor Joe Klewicki is head of the School of Electrical, Mechanical and Infrastructure Engineering in the Faculty of Engineering and IT of the University of Melbourne. He is also the Faculty Director of Infrastructure. He is a Fellow of the American Physical Society, the American Society of Mechanical Engineers, and the Australian Fluid Mechanics Society. He is also a distinguished alumnus of the Michigan State University, MSU, Department of Mechanical Engineering, and received his bachelor and master and PhD degree from MSU, Georgia Tech, and MSU, respectively. As a researcher, Professor Klewicki specializes in experimental methods in fluid mechanics, turbulent and unsteady flows, vorticity dynamics, boundary layers, and atmosphere surface layer phenomena. He conducts much of his research on the fluid dynamics of turbulent shear flows, with a special emphasis on wall-bounded turbulent flow and their Reynolds number scaling. His research involves both analytical and experimental studies, including the development of experimental methods, and involves other complex and turbulent flows. More recently, he has also begun to study phenomena especially relevant to geophysical flows, namely those that include effects of three-dimensionality, stratification, and rotation. So it's with great pleasure that we host today Professor Klewicki for the first webinar of the season. So Joe, I think you can, if you agree, you can start with your seminar.
Okay, thank you, Francesco, and thanks to Christos for having me here. It's been a great visit thus far, and finally getting some time to actually look at some data, so it's been wonderful. I'm not sure who's online. I'm pretty sure nobody in the room has seen this talk, but there may be some folks online who've seen a version of this. I've given it a few times, but I'm not too apologetic about that because I tend to not give talks more than once, and then I have this collection of talks that I've only given once. So today I'm going to hopefully convince you that we've devised some turbulent channel flow similarity solutions. So I'm not claiming that these are approximate solutions. The claim is that these are bona fide similarity solutions to the Rand's equation, and you'll be able to make a judgment of that by the time I'm done. Okay, so what we're going to talk about is scaling and invariance very generically. And then we'll talk about the steps needed to obtain these similarity solutions. There's one primary assumption that's well supported analytically and is testable assumption. So we'll be able to put some accuracy on that assumption. There's a decision that has to be made that limits the scope of the analysis, and then the rest is analytical. And then we'll look at the analytical properties, and we'll do some very close comparisons between DNS data and these solutions. We'll use the large Reynolds number DNS of Yamamoto and Tsuji. And we can talk a little bit about this. This was the highest Reynolds number DNS at the time I did the analysis. There's some that are slightly higher. There are some questions about this DNS in that it's a finite difference, but it has very fine resolution away from the wall, and that makes it quite attractive because the action I'll be looking at is mainly away from the wall. And then I'll make some concluding remarks. Okay, so we'll start very simple here. So we're going to talk about invariant representations of the equations, but we'll start with a simple concept here of just a circle. And so it has its two characteristic properties. There's a diameter and then a circumference. And if I take the circumference and I divide by the diameter, I get pi. And that's true for any circle. So that's an invariant representation of a circle. So pi is an invariant representation of a circle. You give me a circle and I'll give you pi as this relationship, and it holds for any and all circles. Okay, so that's basically the idea that underlies scaling in fluid mechanics. And so when we talk about scaling in fluid mechanics, we're really talking about invariant representations of the equations and then the solutions of those invariant representations. And there's well-defined mathematical theory, it's Lie group theory, if you really want to get into the details on why or what underlies these scaling ideas. And what we're interested in fluid dynamicists is be able to predict into parameter regimes, for example, that we can't access experimentally or numerically. And so the scaling problem allows us to do that if we can get the proper invariant representation and the proper normalizations. And they become invariant then to changes in the governing parameters. I think an important point is if the governing equation doesn't admit an invariant form, and there's, that's a complicated question because sometimes it's just a matter you can't find the invariant form, then there's no reason to expect it can be scaled. In other words, all scaled solutions come from equations that can be written in an invariant form. Okay, and so anybody who's done experiments here is familiar with the empirical test. So you have some velocity statistic or some statistic of the turbulent flow field, and you have some way to normalize it. So you put a star on it once you make it non-dimensionalized using your parameters of interest. And so you get that this quantity is now normalized, say it's a profile, so it's with distance from the wall. If it doesn't change, then the empirical test says, oh, I've got something that's a candidate anyway for an invariant representation of that variable. Now, experimental data can never prove a scaling. They can prove the negative, but to really prove it, you have to come up with an invariant form of the equation and solve that equation. If you really want to mathematically prove it, you can give very strong evidence that empirical data, that's beyond its scope. Okay, so here's a nice example of an empirical test. So here's some laminar boundary layer data that we took at different Reynolds numbers. So big C, well, the circumference, right? And then we're going to go ahead and represent it in the Blasius coordinates. And so now you think pi or C over D, right? And you get this invariant representation of the laminar boundary layer by normalizing it by these special variables. Now, this is a particularly interesting example because it has some relevance to what we're going to do with the channel flow. So if we just look at the Blasius boundary layer solution, so we have the Blasius boundary layer equation, and then we can put it into stream function. You've got some boundary conditions. You undergo a similarity transformation. You end up with a nonlinear ODE. You can't solve that in a closed form, but you can integrate it using MATLAB, for example, and you get a universal curve that was represented on that previous plot. Okay, so that's all really good. Now this represents is that an exact equation? So flat plate, laminar boundary layer, is that an exact equation? I know I got some graduate students in here. So is that an exact equation? What is it? What is this equation? It's the Blasius boundary layer equation, right? So exact or not exact? Oh, we get a bunch of cowards in the room here. Nobody wants to commit. So this is an approximate equation. It's the asymptotic representation of the it's the high Reynolds number asymptotic representation of the Navier-Stokes equation. So if you take the Navier-Stokes equations for a thin shear layer along the wall, you let the Reynolds number run to infinity, then the Navier-Stokes equations approach this equation. This has relevance to what I'm going to be talking about today, in that I'm going to be talking about exact solutions to an approximate a leading order representation of the equations, and that leading order representation becomes better as the Reynolds number goes to infinity. That's different than other representations you might see of a boundary layer using analytical or semi-analytical methods where they might use matched asymptotics. So that's an approximate method for an approximate equation. I'm going to be talking about an exact solution to an approximate equation, and that approximate equation gets better as you crank up the Reynolds number. Okay, so what are we interested in? Well, we're going to focus on the inertial sublayer in physical space, but actually some of the solutions will run all the way to the channel line center. And we'll be considering channel flow. And the inertial sublayer, so this is the region that's far enough away from the wall to be inertial, but interior to the flow, so it minimally sees boundary condition effects. And as the Reynolds number gets large, that insulation from the boundary effects gets smaller and smaller. This is like the inertial layer in spectral space for the people who work in that area. Okay, and here's the nomenclature we'll be using. Okay, so let's talk about how this similarity solution is constructed. And I'm not going to go into all the mathematical details, but hopefully I'll give you enough so you get a flavor for it. Okay, so here's the problem: turbulent channel flow. So it's the typical turbulent channel flow, infinite length, infinite width, driven by a pressure gradient. This is the spatially uniform pressure force. And here's the mean equation. So if we take the Reynolds average Navier-Stokes equations and simplify it for this flow, you've probably all seen this equation before. And so we've got the mean effect of the turbulent inertia, the Reynolds stress gradient, is equal to a pressure force and a viscous force. That's all very straightforward. Okay, so if we go ahead and normalize this by our inner variables, so u tau and nu, I had those up previously, then we'll call those the plus variables. So we have our viscous force, our turbulent inertia, so that's the gradient of the Reynolds stress, and then you've got your pressure gradient, and I'm going to associate that with a small parameter epsilon squared. Okay, so now there's only 3 terms in this equation. Unfortunately, there's 2 unknowns. And that's the crux of the problem we're dealing with here today. So if we take the ratio of the viscous to the turbulent inertia term, and we just plot this out, then there's some important information that's derived. Okay, and this I suppose you could think of it as the empirical input to this. Now we don't need to know the scaling behavior of this with Reynolds number. So these are 3 different Reynolds numbers shown here. So what does this tell us? Well, if this ratio is at 1 or close to 1, that means that this term is negligible, right? And then we see that as we move in, so that's what we'd call layer 2. If we move into layer 3, then we see, well, it's most appropriate. This layer 3 is written for this highest Reynolds number case. We see that these terms switch magnitude, right? So that the viscous force term gets small relative to the turbulent inertia term. And then the turbulent inertia term balances the pressure gradient term as we move out of layer 3. So what happens is we go into layer 3 with the viscous force and the turbulent inertia force being essentially equal and opposite. All 3 terms are leading order across this layer 3. And then as we leave layer 3, then it's the balances between the 2 inertial terms. So this outer line here, really represents the beginning of the inertial layer. That's where the dynamics are inertially dominated, because the viscous term loses leading order importance there. Okay, this structure is important because what happens in the channel flow is that this structure for the overall flow actually happens as a function of scale, as a function of distance from the wall. And what I'm going to do is construct a similarity solution with a local scaling layer like this layer 3. Okay, and I could show you how you could make this layer 3 invariant, but I'm going to show it to you for the whole sequence of layers. I'm going to write an invariant equation across a continuous hierarchy of layers, and that will represent the basis for our similarity solution. Okay, so how do we do this? Well, if we go ahead and plot the viscous force and the turbulent inertia and then the pressure gradient, and this is a pretty low Reynolds number, because if I did it at high Reynolds number, everything would be really scrunched down here on the axis. as we move across layer 3 and into layer 4. So what we do is we construct a new coordinate system, and that coordinate system keys on the monotonically decreasing portion of this turbulent inertia term. Okay, and it's basically a coordinate transformation. We're going to use it as a surrogate, or we're going to use the properties of this to renormalize the distance from the wall. Okay, that's probably one way to think about it. And the way the construction works is that you can identify any point on this curve, and these positions are called beta. So there's some value of this on this curve. It's important to do it on the monotonically decreasing part. Otherwise, you wouldn't have a one-to-one transformation between the y-axis and this curve. Okay. And for each one of these positions, there's going to be a layer, like layer 3 is for the overall flow, where there's a balance exchange, where the leading order balance goes from viscous to inertial, and that happens as a function of scale. And so what we're going to do is we're going to be able to, and that happens over a finite width, just like across layer 3. So you can pick any point on this curve, and so there'll be a layer there. And that scaling will hold to leading order over a finite width layer. And that's important because it allows us to represent a discrete representation of this layer structure rather than a continuous one, but it's actually continuous. So there's going to be a position and a layer width that's associated with every point on this curve. The width of this layer has to do with the rate of change of slope of that function. Okay, so how do we construct this invariant solution on each one of these layers? Well, you can rewrite in terms of coordinates where y beta is the y plus position at some point on that curve. Okay, and if you put in this finite transformation, I won't go through all those details, and you plug it in here, you can get an invariant form of the equation where all terms are order 1. Okay. And this has been verified. You can actually look at the magnitudes of the different derivatives and look at the bounds. And this is valid on each one of those layers. And it's subject to these stretching parameters having this representation. Okay, if those are satisfied. So you notice we got a floating parameter here, lambda, and that's associated with velocity scale. And this is important, and this is where we're going to limit the scope of the analysis. If we limit the scope of the analysis to lambda equal 1, that says that u tau is the characteristic velocity, and that leads to a logarithmic analytical solution for this equation. Okay, it turns out we've looked at some pressure gradient flows. I won't talk about that today. And lambda could be variable because you could have multiple velocity scales. And I can revisit this. This is actually testable, and I'll comment on this at the end, that it's true that u tau is the only velocity scale for channel flow.
So u hat is in wall units.
This is in
Y hat, sorry, y hat is
y hat is, well, there's a transformation between hat and,
so it's in wall units.
well, it's in using u tau and the characteristic length scale. Oh, the local characteristic length scale. Okay. Okay, so one of the things that's important here is now we want to try to identify the positions of these layers. There's an anchor and then there's a width as a function of beta, as a function of moving down this curve. And this is an exact representation, and what it does is it actually defines what this T beta is. So think about this T beta function. It's just a mathematical construction. It goes through its peak at every one of those points on the beta curve. So it looks like the Reynolds stress, right? The Reynolds stress goes through its peak in layer 3 of the overall flow, but on each one of these beta layers, this T beta is going through the peak, and thus you end up with that, which is the definition. So it holds, it's mathematically exact. Okay, so we start with this, and we differentiate with respect to beta, and we get this equation, and then we normalize in the local variables. Remember, beta is related to the width of the, well, I'll show that beta is related to the width, and this y hat equals 0 is the anchor position on any arbitrary layer. So if y hat equals 0, it says you're on one specific layer and you're at that point that's the anchor position. It could be any point anywhere in that layer, actually. It's easiest to just do it at the beginning of the layer. Okay, so you have this expression, and now we know that this quantity A beta, which is the curvature of the locally normalized Reynolds stress on that layer, is order 1 for all beta, meaning it's bounded. We know this, and we know that because we can write a similarity solution, and so everything is bounded in that similarity expression. And I can go into details on that if you want. And this is going to get us to really the one assumption that has to come. So we know it's bounded. We know it's order 1 for all Reynolds numbers. Okay, and we can then write dy beta d beta is equal to this. Now we get to the one key assumption. Okay, and this is testable, and we'll test it here with the data. Is that we assume, so this is this expression I had before, that A approaches a constant on this interior domain as the Reynolds number goes to infinity. Not just bounded, but actually goes to a constant. Okay, and there's good reason to believe this, because if you have, suppose you wanted to create a facsimile of a similarity solution in the laboratory. Suppose you wanted to do Stokes' first problem. So you have a big plate. We'll say you start with a small plate, and then you pull it, right? Well, if you have a small plate, that's going to be a problem, right? Because you've got edge effects. But as you make the plate bigger and bigger, you're going to get a diminishing edge effects, right? Well, this, as the Reynolds number goes to infinity, you're getting that interior domain becoming more and more insulated from the boundary effects. And those boundary effects are the only thing that can disrupt the self-similarity on the hierarchy layer, because on each one of the layers, we were able to write it in invariant form. And so the only way that invariance can be disrupted is through boundary effects. Okay, well, if we have A as equal to a constant, then we can integrate this thing. And if we integrate it, we show that the positions of the layer are given by this, and the layer widths are given by this if you rearrange it. So you can just, because there's a one-to-one transformation, you can just say there's some y plus, and that y plus equals y plus beta, and thus you can write the layer widths become a linear function of wall distance. This is in this theory, this is the origin of distance from the wall scaling. Okay, this is how you get analytically how the equations admit distance from the wall scaling. It's these layer widths scale with distance from the wall. Now you can actually rearrange this. You can write it this way, and this is phi, and it's phi sub c because A is a constant. If A is not a constant, it would just be phi, and we could define it in the region everywhere. Turns out that it only reaches constancy on the inertial domain. So once you get in beyond peak in the Reynolds stress, and the flow is in that domain where the viscous force is subdominant, and we'll show that in a few minutes. But the thing I want to show here is that if we take Y and normalize it by W, then we get this quantity phi, and I called it phi because Paul Fife was the applied mathematician who came up with most of this, or the basic idea of it. It turns out that this phi is actually related to another phi, and we'll get to that. Okay, so this is testable because we can measure W, and we can directly see if that quantity is constant. Okay, and there it is. So you can just compute W. These are from different DNS, so they go from about 550 to 10,000. And so this is the region where you get this linear variation. And how linear is it? Well, if we take W and we normalize it by Y, you can see, and it's a function of Reynolds number, that you flattens out here and becomes very close to this phi, and I'll talk about this phi later on. Okay.
Can you say again how you calculate W?
W is just equal to beta to the minus 1/2. So it's equal to dt dy plus epsilon squared, so 1 over Reynolds number to the minus 1/2. Or equivalently, it's equal to the other side of the equation, which is minus d squared u dy squared to the minus 1/2. So it's very easy to compute. This is computed using the velocity because it tends to be a little less noisy than the Reynolds stress. Okay, and so we're going to go ahead and explore this quite a bit more. And in fact, we're going to look precisely at the slope of this and make an assessment of how accurately we can measure W. Okay, so now with this similarity construction, we can take the once differentiated form of the mean momentum equation, which gives you the vorticity equation. Okay, and this allows us through this fundamental representation of similarity, the quantity here, we can either construct an equation that's purely in terms of U or purely in terms of T, the Reynolds stress. And this hopefully will give you some confidence. This is a genuine similarity solution. I'm not solving for the velocity and then plugging that velocity in and getting the Reynolds stress. I can write a separate equation for the velocity, solve that. I can write a separate equation for the Reynolds stress and solve that. And they're copacetic. They agree with each other. They don't violate, they don't contradict each other. And if we do that, well, we integrate the velocity equation, we get a logarithmic law, but with a linear term here. And the other thing to notice is that this phi sub c shows up, as you might expect, because it's the fundamental parameter defining the self-similar behavior. It shows up here, where you'd expect to see the von Karman constant. Okay, and it shows up here and here. So it's everywhere in this equation. In the following analysis, you'll see that this phi sub c shows up all over the place. Okay, so the last thing I'll talk about before we start looking at some of the specific properties of these solutions is that because, although it's a continuous hierarchy, to leading order, that invariant form is valid over a finite domain. So you pick a spot, there's a length scale associated with that, and the invariant form is valid over that finite domain. And so you can create a discrete representation. So you get some distance from the wall y, and then you add the w associated with it. So that's the w associated with that y, and it gets you to the next y. Okay, so you just stack them up. And so this is data from the Yamamoto and Tsuji, and these are actual w's. Right, so these are W picked off of the off that graph I had before, and these are just represented. So this is the beta curve, and these are the W's associated with those points. And I'm just saying, instead of having using a continuous representation, I can write an invariant form over that width, and then I can stack it onto the next one and write it over that one, and allow you to do some algebraic things, rather than have to deal with continuous functions all the time. Okay, so let's look at some of the properties.
The form is true to leading order, you said, to leading order.
Yeah. So the representation on, because remember, we're looking at the scaling of the mean momentum equation as the viscous term transitions from dominant order to subdominant order, but that viscous term is still non-zero, right? But as the Reynolds number goes to infinity, that level of subdominance becomes more and more and more, right? And so that's how this solution is, refined. The inertial layer truly becomes fully inertial. There's a diminishing effect of any sort of remnant viscous state. By the way, the reason it's so difficult, or the challenge of coming up with a good argument and good solution for the log law is because the logarithmic law happens on a domain where the velocity term in the equation, so the viscous term, is subdominant. So you're actually looking for a second order solution, right? It's not in a region where it's a dominant term in the dynamics. That's why it's been so elusive. Okay, so this may be a little surprising to you. And I don't know, can I blow that up? So these are you all recognize these. These are the mean velocity profiles. And the colored lines here are representations of the solution for the given Reynolds number. And they all begin at the outer edge of the layer 3. So that's where the inertial layer starts, and they end at y over delta about 0.125, and I'll give you a justification for that. So the beginning of the inertial layer is truly where the viscous term loses leading order. And so you can see they're here, and this is just an expanded view, and hopefully I can I expand it? I can. Okay, so one thing that's a little surprising here is that, this u plus y plus thing, that's supposed to be invariant, right? Well, these curves don't quite fall on top of each other. All right, and you can also see that, so here's like one of the low Reynolds numbers, log layer, and here's a high Reynolds number one, and they don't even overlap with each other. And the construction of this similarity solution says, actually, if you want to do the proper invariant representation, is that you would use the velocity at the beginning of the inertial layer, and you'd line those up, right? And you do that, it's a square root Reynolds number scaling on that, and that would line those up, okay? And then asymptotically, that velocity at the beginning of that layer becomes a constant value, and so they'd all have the same starting point, and then it would line it up. But that's hard to describe because everybody's so familiar with the u plus equals y plus representation. But the point here is that they don't fall on each other, on top of each other, because they're actually not properly normalized except in the infinite Reynolds number limit. See if I can get this to get small again. Okay. Now I've done it. Okay, good. So this plot here is an evaluation of some of the important terms here. So here's the velocity equation. And, if we're going to recover the classical log law, we got to get rid of this term. So what does that mean? That means it has to decay with Reynolds number. Well, we know it decays with Reynolds number because if you take the derivative of this, then C2 must go to 0, right? As the Reynolds number goes to infinity, otherwise it would blow up. The issue though is, does it go to 0 at finite Reynolds number? And it needs to decay faster than 1 over Reynolds number, and it actually decays something like Reynolds number to the -2. So it decays. So this term goes to 0 at finite Reynolds number. Okay, and that's what this curve here tells you. This is a measure of the leading coefficient, and you can see it's approaching this dashed line here, which is this analytical expression. I'll talk more about that later. And then the other terms settle in, and some of these observations are pretty you're pretty familiar with. There's an offset here, and I'll talk a little bit more about that later when we talk about evaluating the log law. Here's the Reynolds stress profiles and the Reynolds stress solution. I want to impress. So here's the linear representation. And what I've done is stacked up some layers starting at the peak. And you can see there's that little yellow one, and then they get bigger and bigger. These are the W layers associated with that. Okay. And then here in the bottom, I represent, here's the actual DNS solution. So these are the data of Yamamoto and Tsuji. The dashed line is the solution. Okay, so just so you get a sense of the quality here, the agreement of this solution with the DNS is less than 1 part in 1,000 anywhere on that curve. So if you take the worst case, it's less than 1 part in 1,000. So that's pretty good.
But that's the part of the Reynolds stress which is equal to 1 minus y.
Well, that starts out here. So there's curvature in there. Okay, and that's what it's capturing. The other thing is that if you do a little bit of analysis of this equation, you can show that, well, if you do analysis of the equation, you can show that the peak in the Reynolds stress goes like some constant times the square root of Reynolds number. And you can actually show that this constant approaches phi sub c like 1 over Reynolds number. So as the Reynolds number goes to infinity, it becomes equal to phi sub c. And the phi sub c value that I'll give you later on is, so this is a DNS, and out near the peak in the Reynolds stress, the spacing in the DNS grid is still less than a viscous unit. So it's like 0.94. And in the data they list, there's 2 peak values. And the position of the peak here is between those 2 peak values. And I'll give you a representation of the error associated with that. So it's kind of, and I should admit, if I take other DNS that are recent DNS, it's not that perfect. Okay. That to me just shows that there's still very small differences between DNS. Okay. The other thing you can do is an analysis that says the deviation of the maximum value of the Reynolds stress from 1, which is the asymptotic value. And here I show a few different normalizations. The thing you'll notice here is that there's the data point at Reynolds number of 4,000 from Tsuji and Yamamoto seems a little low relative to the other ones. And the black line is if I fit them all, just free fit them to the equation here, some power law, which we know it must be. And the theoretical prediction is that it should be 2 phi for the constant and 1/2. And if we set the constant equal to 2 phi, well, equal to the conjectured value for the asymptotic value of phi sub c, then we get a value of 0.4999. If we set, let me see, the unconstrained one has a value for the exponent of about 0.52. The theoretical value, if we put it there at 1/2, then we get another coefficient. But you can see they all are very close. Okay, the other thing that the theory allows you to do is objectively estimate the outer edge of the log layer or the inertial layer. And there's a couple ways to do this. It's basically you want to measure, and Christos just mentioned this, you want to measure the curvature of that Reynolds stress profile, because when the curvature stops, then, well, at a minimum, you can't assess the log layer because it depends on the curvature of the Reynolds stress in this theory. That the reason you get logarithmic behavior has to do with that curvature of the Reynolds stress, because it's that curvature that leads to the W distribution having a linear dependence with distance from the wall. The other way to do that is you can just look at the ratio of the delta T across any layer with distance from the wall. Turns out the delta U on any layer is constant, and it's a function of phi. Whereas this is not constant, but when you get out to where you can't measure the curvature anymore, it becomes equal to phi. Okay. And so if we look at these data, and I've looked at a few other data, it's about at a 1.125 plus. It may actually go up further. It's just that you get into the noise of the data, right? The curvature becomes so mild that you can't measure it. Okay, so that allows us to properly define the beginning of the log layer, this is where the viscous force becomes subdominant, and properly define the outer layer, the outer edge, that's where you can practically you can no longer measure the curvature. Okay, so the last thing I wanted to talk about is estimating this key parameter, phi sub c, which is really at the heart of the similarity transformation. And there's a number of ways you can do this. I already talked about one, right? You could just go ahead and look at the position of the maximum, plot it versus square root Reynolds number, and measure the coefficient out front. But that's not a very reliable thing because you got one data point that tells you, right? That's not very good. You can look at a modified indicator function. Okay, this is sort of the classical way to determine logarithmic dependence. And then we also have the profiles to look at, right? So you can fit these profiles over a considerable amount of data points and make an assessment of that. We'll look a little bit at this, but then we'll actually look at some fundamental definitions, right? So if it's a similarity solution and I can get U and I can get T, or the Reynolds stress, then I should be able to use the U profile to get phi, and I should also be able to use the Reynolds stress profile to independently get phi. Okay, and we'll do that as well. But before we do that, let's go ahead and take a look at some data that's out there. So these are just for pipe and channel flow. The reason I throw pipe in there is that you can write the pipe flow equation to look exactly like the channel flow equation. Well, they may approach their asymptotic condition differently, but you can write them exactly the same. And what we see that it's interesting, Von Karman, his original sort of estimate was 0.38, and we have deviated from that, and actually there's papers out that says it's more like 0.43 or something like that. A lot of the more recent measurements seem to be agreeing with what Von Karman thought to begin with. So, you know, what comes around, I guess. The ones I'll point out here, so this was an estimate using the present theory, using the data of Jimenez. And these are estimates using the same measurement of the W profile. Okay, so just really quickly, I'll talk about the mean velocity and Reynolds stress gradients. So here's du plus dy plus, and I won't blow these fits up. You'll just have to take my word for it. They basically fall right on top of the line. This is over the inertial layer. If we represent it this way, then this is actually an invariant representation for the overall momentum balance. And thus, at any Reynolds number, this point here, phi and phi will fall at the peak of the Reynolds stress. Okay, so that coordinate at any Reynolds number under this normalization will fall at that point. If we look at the Reynolds stress gradient profile, and this is fit, the reason it works all the way out to the outer edge is that the transformation, the intermediate transformation for the overall flow, the gradient has the same representation as outer normalization. And so you pick an anchor point where the intermediate scaling works, but since it's just the gradient, when it switches over to outer scaling, it has exactly the same numerical value. It just works all the way out to the center line. This has a deviation of, again, less than a part in 1,000, except maybe right out here, you can see there's a little notch up there. Okay, let's talk about the modified indicator function. So the theory that we have here says rather than du plus dy plus equals 1 over kappa y plus, there's some constants in here, and that's a problem. And I'll show you how this is. And so if you wanted to do the indicator function, you'd represent it this way. And you know, whenever you're trying to evaluate something, if you got adjustable constants, well, you can make it work. But then the problem is you got these constants. And so here's in the gray, the light gray is the indicator function from Tsuji and Yamamoto. And what I've done here is I've held one of the constants, or set one constant equal to 0 and adjusted the other constant and then reversed that. So in this case, the dashed line, we took the C2 and set it equal to 0, and then adjusted C1 by a value of minus 3.178. That's equivalent to shifting that offset in the log law by 3 viscous units. Okay, and if you shift it by that, then you get this flat region across the inertial layer. Okay, similarly, if I hold to get rid of the other constant, we're going to set C2 or C1 equal to 0. I modify C2 and set it equal to 2.65 times 10 to the minus 5, so it's pretty small, right? And I get this curve. Okay, so rationally, the estimate for kappa is, or phi is somewhere between those two estimates. Okay, I think the thing I want to point out here, though, is that this indicator function is very sensitive to those constants. Okay, so it would be better to be able to make an evaluation that doesn't depend on those constants. And that gets us to the fundamental definition, right? No constants, we can just go ahead and measure it. Okay, so here's the W profile from the delta plus or RE tau 8000. And there it is there. And what I've done here is blown it up and offset it for different curve fits. So this is the red curve fit of the W profile on the inertial layer. So it goes from about 220 to 1,000 in Y plus units. And then these are fits, blue and the green are fits over bigger domains, and they've just been offset. So you can see if you blow it up enough, this curve up here gets some wiggles in it, which you can see there. And so if we fit this linear function over the inertial domain, then we get a value of 0.61 for p sub c to the minus 1. And this is a standard deviation of that. Okay. And so that's the deviation. So these are the wiggles there. The deviation from linearity is less than, well, it's about 4 parts in 10,000, right? So it's, and this is the assessment of how good was that assumption, right? How good is the assumption? The assumption, the linearity of this is the assumption. If this is linear, then the assumption, the primary assumption that I said, that function A or phi sub c becomes a constant as the Reynolds number goes to infinity. So this is in, less than parts per 1,000. Okay, the last thing I'll show, and maybe it's haven't you seen before, is that if you take the T plus profile and you write it in its asymptotic form, so that last term simplifies and the constant goes out of this term, because if you're at infinite Reynolds number, some little constant isn't going to make any difference. Okay, then what the theory says is that T plus, well, once you have this expression, you could say T plus on one side of the peak of the Reynolds stress is equal to T plus on the other side of the Reynolds stress, and you can thus set those two equations equal to each other. And then you can write an expression for, so to solve that, you can write an expression for phi sub c. Okay. And so we can just go ahead and do that. So here's a blow up of that Reynolds stress profile in the vicinity of the peak. And I'm going to pick a point here. I'm going to pick a point here at the same T value. I take the geometric mean of those and I get that point there. You can see it's not quite on the peak. It's a little bit shifted, right? And I can do that for different points here. And I did it for 8 here. And if you do the 8, and you take the average of them, you get a value of, well, phi sub c is 1.695. So 1 over that is close to that other value I got from the W. Okay, so this is the independent way to do it using the Reynolds stress profile. Okay, so if we look at all the different ways that we measure it, then so here's just picking off the peak, and you can see that there's, even though the spacing, remember I said that the peak fell between 2 points that each had the same peak value. And so it was somewhere within about 0.94 viscous units. And that's the uncertainty represented by that. If you are, so it's a small value, right? And then if you measure it relative to, and I'm measuring it relative to phi. Phi is, does anybody know what that number is? That's the golden ratio. Yeah, and I'll show you why this golden ratio pops out here. It's nothing mystical or anything. It just has something to do with the way this layer hierarchy is constructed. Okay, it's actually quite simple. But you can see that when you go to the more fundamental ones, we get even closer values there. So that's a summary of what we find in terms of phi sub c being, number one, a constant, and actually very close to the analytical conjecture that I'm going to talk about a little bit here at the end. Okay, so let's just talk about this geometric structure. So we'll go back to the discrete representation. So the discrete representation says, I'm going to go some y distance, and then I'm going to tack on a w, right? So there would be the anchor point, and I get to the next y, right? Well, if you look at the construction of the golden ratio, you have some distance, and you add it to another one, and you get the total. And then if you add other constraints, you say that A over B is equal to C over the larger part, A, and the part I already talked about, A plus B is equal to C, then that's exactly true. Okay, that's what's required of the golden ratio. In this case, we've got y over w is equal to phi sub c, and we've got y plus w is equal to y plus 1. On the other hand, we've got this, it's not exactly, it doesn't, I've gone around and around and around, I can't quite get this, right? But the best you can show is this, as far as I know. Okay, and so if this quantity approaches 1, then phi sub c is equal to golden ratio. Okay, and it's simply because it's a statement that the layers not only scale with distance from the wall, but they're self-replicating. It means that the next w is equal to the previous y, right? So it's an additional set of self-similarity. It's like distance from the wall plus, right? It has an additional feature there. And the curious question to me is, as the Reynolds number goes to infinity and there's nothing interrupting that self-similarity, what would prevent it from reaching that state? Right? Not so much that why does it reach that state, but what would prevent it? It's sort of the natural thing you should expect. Okay, the last thing I'll just mention, well, let me go back. Whoops, back. So there's a couple ways you can sort of hone in on how this construction and how the layers construction connects to the Reynolds stress distribution. I'll just return to that really quick. So one of the things is you can, in the analysis, you can write an expression for y1 in terms of some phi sub c that you don't know. Okay, and then the question is what is the y1 that falls on the layer that leads to an integer number of layers spanning the distance between 2 points on this curve, or 1 point on this curve. Okay, and so you can do that for y1, and you can get an effective phi, and you can also write an expression for y2 and get an effective phi. All right, and now you start going up the curve here, and so you pick a point here, and this says, well, the what maximum, according to this prediction, or the formula that you get for that's based upon y1, you'll get a prediction for the peak, and you get a prediction for the other part of the curve. And so now you can start moving up this, and if you see, if you move up, these points move, this one moves toward the center, this one moves toward this side, and as we move up,
you get different values of phi that are associated with that. And when you get to phi equals the golden ratio, there's the starting point for the circle, right? Its prediction for the peak, which is pretty much right on. And you can see it's slightly off for the other side, right? So if it was exactly that. And similarly, if you do it on the other side, so that's why you see this center diamonds cross over these right at the position where a single layer spans the curve. Okay. So it's this layer hierarchy structure is actually embedded in the Reynolds stress distribution. Okay, so let's do a little bit of a critique. So the equation or the development of the analysis rested on some empirical. And this method starts by using data to determine the progression of leading order balances. We didn't have to say anything about those leading order balances. We just needed to know that near the wall, the viscous force was important. There's some region in the middle where all three terms are leading order, and then there's an inertial region. With that information, you can just then go to the equation. The scaling coefficient for U is lambda equal 1, which says that U tau is the only velocity scale. This is testable, right? And it's testable because the layer width would not be invariant under this scaling. In particular, layer 3 for the overall domain is one of the layers on the hierarchy because it falls in that domain. So if it's actually one of the layers. And so we looked at data up to about 560,000. So these are the McKeon pipe flow data. And according to the theory, the delta U across the layer, I can't remember this formula, it's like something like phi squared log phi, or maybe it's phi log phi squared. It's a simple function of phi. It's like 1.25, right? We get a value that's somewhere between 1 and 1.4 across those. So that's the experimental uncertainty up to that Reynolds number. So there's no reason to believe that that lambda is not equal 1, meaning that the friction velocity is the characteristic velocity for this flow field. And then the last one is that A approaches a constant as delta plus approaches infinity. That's equivalent to the slope of that W profile approaching a constant. And according to the Yamamoto and Tsuji data, that is deviates from a linear function by about 4 parts in 10,000. Okay, so what does this have to do with other wall flows? Plane Couette flow is aspirationally logarithmic, and that's because it always has a leading order viscous term. There's only 2 terms in the equation, and so you can never get rid of the viscous term in Couette flow. Pipe flow yields the same results because you can write the equations the same. The wall curvature does throw into questions whether they approach their asymptotic state at the same. For the zero pressure gradient boundary layer, it has a mean inertia term rather than the pressure gradient term. And so the shape, actually, the Reynolds stress profile is quite different out there. I had a student, Caleb Morrow-Winter, who did some analysis of this using some high Reynolds number boundary layer data. And it was able to show that the MI term is shape preserving and scales with delta. And you can then go through a scenario where you transform this MI term, and then you can show that it has the same similarity structure, but maybe with a slightly different position, slightly shifted outward for layer 3. So the summary is the solutions to the channel flow Rand's equation exhibit nearly exact agreement with the DNS. The key assumption of the present approach is satisfied within less than 0.1% at that Reynolds number. The logarithmic profile is shown to occur because of linear variation of the curvature of the T, or the Reynolds stress profile. The inner and outer boundaries are well defined. The properties of the asymptotic T profile are shown to analytically connect to the underlying layer hierarchy. So this phi shows up everywhere in this flow. And there's multiple ways to estimate phi, and using curve fits, using many data points, different functions. And if the hierarchy becomes self-replicating, as I described previously, then this has a analytical solution for kappa, which is then like 0.381966. And then ongoing work is looking how deeply these similarities might be embedded in the turbulence itself. And I'll stop there. Thank you.
So thank you very much for the presentation. I would say we can open the stage for questions if you agree.
Yeah.
There is already a question from the virtual audience, so I think we can start with that. So Alan, please go ahead. Just unmute your mic and open your camera and ask the question. Go ahead.
Well, it's very interesting to see how, Joe, you've developed this since we discussed this a long time ago. And but one question comes to mind is this layer hierarchy concept. It seemed to arise from particular features, such as you mentioned, the subdominant role of viscosity that requires a kind of a subtle treatment. So my question is this layer hierarchy a mathematical feature that arises uniquely just for this problem, or is it one instance of something that has more general application? And I'm talking about potentially just from a mathematical viewpoint, not necessarily limited to fluid mechanics per se.
That's a good question. We've only been able to identify this particular flavor for this flow, but I think the bigger picture here stems from the work that Paul Fife did, where he used this methodology called scaling patch method. And there is a more rigorous mathematical treatment around that, where you estimate the magnitude of derivatives, and they can't be too big and they can't be too small. And what you're basically doing is looking for domains where the normalizing variables keep things bounded. And you know, T.A. Way, of course, he's used this methodology in a whole number of flows, jet flows, wake flows, stratified flows. And he's used it to find these scaling patches. And the layer hierarchy here is nothing more than the continuous concatenation of scaling patches, where you find the natural length scale and the natural velocity scale over a domain. If you want to think about it, the laminar boundary layer example that I started with, that's a single scaling patch. That is, you write an invariant form of the equation over the whole domain. This is simply a representation that says, no, the length scale, the characteristic length scale changes. So you have to have a sequence of scaling patches. So I hopefully that at least partially answers your question, Alan.
Okay, great, thanks.
But I wasn't clear why the scale u tau doesn't change with you said that the scaling for the mean flow is always lambda equals 1.
What that says is that there is no other characteristic velocity. It says that it's u tau.
You cannot imagine u tau multiplied by a very weak power of Reynolds number. I know it makes no sense, but they have to do with the very large scale motions, which actually bring information of what happens out there.
Well, I could physically imagine that, but the assessment of the data relative to what the theory predicts says if lambda is not equal to 1, then you would expect the velocity increment across the layers to change with Reynolds number. And we look at Reynolds numbers up to 560,000 in friction Reynolds number, and we see no trend. They're all between 1 and 1.4. The theoretical prediction is about 1.25. Okay, so I mean, relative to other theories, most people just assume that u tau is the proper scaling velocity. Now, if you look at pressure gradient flows, I think there's good reason to believe that there's a more complex velocity scaling for that flow. And the reason for that is if you look at the stress balance, so you take the momentum equation, you integrate it once. Well, if you do that for the zero pressure gradient boundary layer, for example, then you just get U tau is the only boundary condition. If you do it for the pressure gradient flow, then you have a non-zero boundary condition related to the pressure gradient out in the free stream. And so it's probably likely that there's both a pressure velocity and friction velocity at play in that flow.
And this hierarchy structure, you have it only in the region of Y, where all the three terms of momentum balance are present.
But so this T beta, right? This construction, that function T beta, you
Oh, there is the Reynolds stress.
T beta is related to the Reynolds stress. So I'll go ahead and draw the Reynolds stress profile. So Reynolds stress looks something like, or no, the gradient of the Reynolds stress, sorry. So it looks something like this. Passes through zero. So there's the peak in the Reynolds stress. That's better. Okay, so so this is T. Well, this is dTdy. And this is the beta. And the T beta profiles would be going through their zero at this point. So they would be coming up and doing something like this. And if I moved out here, it would be doing something like this, because it's going through zero there. And so then you're going to have a layer that's associated with the zero crossing of this function, like this one is for layer 3, right? That's the peak in the Reynolds stress. This is where T beta max occurs. It's going to occur at that position that not perfectly lined up, right? And so this T beta is the peak in that beta. Remember I wrote are they all that way? Nope, we got a good one. T beta, let's see, dP T beta dy plus beta is equal to dt dy plus epsilon squared being 1 over the Reynolds number. Okay, so this is saying, but we know that beta is equal to this. So this is telling you the construction, right? So this must go through zero at that position. Okay. And so the peak in the Reynolds stress for this beta function, this construction, it's saying that there's this balance exchange at a point here, but it has a different length scale associated with it than out here. It's a smaller length scale. Okay, and then if you move outward on this curve, the length scales get bigger, and thus that exchange of balance is described as a function of scale. And then we're able to write an invariant form of the equation. So you can think about this W layer here as completely analogous to the layer 3 for the overall flow, because layer 3 is one of those flows, or one of those layers.
So when we say different length scale, we mean different length scales that depend differently on Reynolds number, for example.
No, well,
They don't mean that.
I mean that there's an angle. You pick a point on this curve,
Yes.
and once you've got that position, there is a fixed W plus that's associated with that. And it relates to, on this plot, it relates to the rate of change of the slope. If it did it in terms of T, the Reynolds stress itself would be the curvature. Okay, so you can see this curve is well, the Reynolds stress has a lot of curvature near the wall and then becomes nearly linear away from the wall. And it's that decay of linearity. And when it becomes purely linear, or then
Same as-
the law, yeah, then you're actually off the W hierarchy. Right,
Okay.
because then you go from the inner peak of this function to the outer peak of this function.
It's mainly around the peak of the Reynolds stress.
Well, it starts at the peak of the Reynolds stress gradient, but you don't start seeing the linearity of that function until the viscous term becomes subdominant. And that happens after the peak in the Reynolds stress for the overall flow. So that's on layer 4. You know, starting at layer 3, in layer 3, and then on crossing to layer 4. It's complicated. But it's I've taught this to undergrads and they got it if you have enough time. Yeah. Other questions?
For the energy, can you see that's
Well, we did it, you know, so if you do the mean energy equation, it shows exactly the same scaling as the mean momentum equations. It's just weighted by U, right?
okay.
So it has the same structure. We did an analysis of the fluctuation and or the turbulent kinetic energy equation. We're able to show some scalings for it, but there's so many terms, right? You know, one of the advantages of this is we've only got 3 terms, and so you can do that ratio and find the leading order balance structure is easy to discern. It's much harder. And energetics is, I find it a bit confusing, right? So the analysis of this flow says, you know, if we do the ratio of the viscous term to the inertial term, we can identify where that leading order balance where the viscous term becomes subdominant, right? That's very clear. On the inertial layer, it's also very clear that production equals dissipation.
Yeah.
So in the energetics, is viscosity negligible? When the 2 dominant terms, one of them is, I mean, if dissipation isn't viscous, I don't know what is. So the energetics seems a little, I haven't quite wrapped my head around that. Except that energetics are different than momentum. They're different than dynamics. Right? You'd agree that production is nominally equal to dissipation.
Well, in a given region.
Yeah.
Which probably overlaps with your.
But that would be on the log layer, right?
Yes.
And that's the inertial layer.
Yeah.
So that's where the viscous term is subdominant, but your dominant balance or budget of the energy says that you have the dissipation term that's very important. So I haven't quite sorted that out. We did do the analysis for the scalar, right? So for a passive scalar, you can show that there's a log law, right? But it's different. And we're able to show that by comparing it with the momentum case, we're able to show that you can write dt dy is equal to d omega z minus w omega y, right? The velocity vorticity correlation. And so if you look at the log law in the scalar case, and Sergio Perzoli had some very nice scalar case where he has it volumetric scalar generation. So it acts just like a pressure gradient. It's not, coming in at a wall. This is generally associated with vortex stretching, or at least if you use the arguments of Pennicus and Lumley. It turns out that there is no analogous term like this in the scalar equation. And so it's just basically, vorticity transport type, or it's, just vertical transport. And so it's the interaction, and thus you get the particular von Karman constant in the momentum case, is because there is nothing analogous. And that's why the von Karman constants are the log coefficients are different in those two flows, because there's nothing analogous to this in the scalar case.
I mean, you could have an equation for the scalar gradient That's what would have something.
Well, you can have the, you have the D, I don't know, it'll be the V C, right? dy, that would be the analogous term here.
Yeah.
And you can write it and you end up with you basically there's nothing because, well, I mean, these two terms are related through a solenoidal condition, and these two terms are related to a solenoidal condition, and there's nothing here. There's no solenoidal constraint on that. Okay, so we basically that the term that would be analogous to this is almost zero in this case, and so it's almost all just basically a vective transport.
Now the usual intermediate static method, going back to Millikan, just says that we all know what it is.
Right.
It gives you a log law as well.
It does.
Your log law is a bit different.
Yeah, although if you look at the, there's recent results that show that there's a, if you do a second order analysis, Jimenez and Moser showed it, you get a linear term. And then recently, Mankiewicz and Nagin, they show that there's a linear term.
You also get the cogent C1 you got because you got one, you didn't get.
Well, I get the offset as well, yes. Right? I mean, the solution is, so, again, I'm making somewhat bold claim. This isn't an approximate solution to an approximate equation. This is an exact solution to an approximate equation. So whatever they come up with the approximate solution to an approximate equation should be a subset of this. And I could give one piece of evidence is that they find, if they look further out from the wall, they find that their log layer has a different kappa, and they're getting values like 0.43 or whatever. They have a recent paper in JFM on this. If you look at the W profile, the W, if I use the curve fits that went farther and farther out, well, you start getting bigger values for P, and thus you're going to get bigger values for kappa. Okay, so my current thinking, biased, is that what they're finding is a subset of this solution. Yeah. Yes.
How does it hold for compressible flows as well?
For compressible flows?
Yeah.
I guess, so for compressible flows, they usually do some sort of Faber averaging, right? Or they have that Van Dries. But I don't know if there's anything that's formally theoretical. I think it works. It seems to work pretty good. Just thinking about a channel flow, if you were in a compressible channel flow situation and you were just driving the flow by the same mechanisms, but you're just starting to get variable, I guess I would still say that some form of the friction velocity is going to be the proper velocity scale, because you're not introducing any fundamental new forces. It's not like adding a pressure gradient where you actually add a term to the equation. But I'm not a compressible flow person, so.
Jim had a question.
Oh. Francesco, is there a question there?
No, I don't see any question on like any virtual question. So if there is in the room, is there someone who would like to ask a question?
Just a short question. You said during the talk that for some of DNS, it doesn't fit so well actually, that the one that you were you able to identify why these DNS does not?
I think DNS is great because, and I think, of course, it gives you three-dimensional fields and all that stuff. But I think one of the things that analysis like this shows is that you can really look at super detailed things just in the profiles, right? So if you have something that predicts some sort of feature or whatnot in the profiles, you can look at. But even there, you have to, there are subtle differences between them. I tend to think that the Yamamoto and Tsuji data do so well for this particular analysis because they maintain such high resolution away from the wall. It's a finite difference solution, but if you compare, for example, their spacing out near the peak in the Reynolds thread, it's less than a viscous unit, but if you look at like Lee and Moser, it's something like 5 viscous units out there. So the delta Y spacing, now they have the advantage of using spectral, right? So it's that gives you some accuracy. And you see that when you go near the wall in the Yamamoto, the peak in the U peak is a little low compared to what you would expect. And so I think the main thing I've learned is that, like experiments, if you look at them close enough, there's little differences, and it really depends on the care it's what's taken in terms of implementing it. It's still not perfect.
If it's also related to the size of the box, actually.
Well, it's funny if you go back. Oops. If you look at this, so the main differences I saw was in the shape, the particular shape of the Reynolds stress profile in the vicinity of the peak. And on the representation I gave you there, where you plot it on a logarithmic or semi-logarithmic, that it's a parabola. And that's a theoretical prediction. And some of them, it's not quite parabolic. On the other hand, if you look at something like the W profile, where I've used Pirozzoli, that was in a pipe, Hoyas, that's a pretty short box, right? So the W profile seems, just calculating that seems to be pretty good in terms of estimating it. It's just that Reynolds stress to compute, and I have lots of experience, Reynolds stress to measure is just very difficult. And it's noticeably how much smoother. So if I plot the second derivative of velocity and I compare it with 1 over the Reynolds number plus the derivative of the Reynolds stress, the derivative, that second, they have to be equal, right? That's the momentum equation. The Reynolds stress one is noticeably more noisy. And so some of it has to do, the noise part has to do with convergence. The shape, I think, probably has to do with a specific implementation of the grid. But, there may be, I haven't been able to find anything, but there may be something that needs to be factored into the analysis to take into account these differences.
Okay. Is there any other question in the room? Okay, that doesn't seem to be the case. So maybe let's check. Let's see if there is some question from the virtual audience. Just once again, feel free to unmute your mic if you have a question. Okay, so maybe I can ask myself a last question then. So starting from this solutions to the boundary layer on a flat plate, could you imagine to generalize the solution, including like higher order effects in the curvature of the plate? So basically, going one order further, and embedding curvature effects in your analytical solutions.
Well, let's see, the curvature would come through the curvature of the boundary. So that would be a boundary condition effect.
But imagining that the curvature is very, very small, it's like an epsilon parameter, not epsilon in the sense of epsilon square equal Reynolds number, but let's call it an epsilon star parameter, which is very small, yeah?
Right. So you have a very mild curvature. I reckon you could probably use the analytical solution as the basis for a perturbation problem.
Exactly. Yeah.
Right? You'd have this as the starting point for a perturbation problem, and then you could just use regular perturbation theory from there. Right offhand, how to incorporate boundary curvature into the, to something that would directly affect the layer hierarchy, nothing comes to mind right offhand. But certainly, when you do a perturbation problem, it's always nice to start with a well-established solution. And so this could be used in that regard.
Yeah, I mean, I was thinking to the case in which basically even a mild solution eventually can produce some effect on some instabilities itself, like sort of Taylor-Gertler vortices, or and eventually be used to have a better prediction of an inset of an instability, for instance.
Yeah. Yeah, I'm not quite sure how this would fit with a stability analysis. I have to think about that. We are doing measurements on a big rotating disk, so we're trying to generate a facsimile of von Karman's rotating disk problems. We have a three-dimensional boundary layer, and you can write the mean momentum equation there. So the analytical reason for wanting to look at that is to try to see if we can extend this technique to a multi-directional flow, where you've got, you're coupling together two momentum equations. And so you've got to then deal with leading order balances on both a tangential momentum equation and the radial momentum equation. That's probably as close as I'm getting to something that you're describing, Francesco. But the idea of using it as a basis for a perturbation problem seems like it could bear some fruit there.
Okay, thank you. So if there are no other questions in the room, I think I think we can close the seminar, and I invite therefore the audience to thank our speaker once again. So thank you, Joe, for the very interesting talk, and it was, as you could see, it triggered a number of very interesting questions and discussions afterwards. So thank you once again.
Thank you.